Good morning, and thank you for coming. I want to, that's why I changed the title of my talk, because I want to talk, first of all, I want to talk about some new things that are happening with the MS-39. But then I want to just quickly, and this would be a 2-hour talk if I went through everything. I want to go through just how extraordinarily versatile this one device is, just this one MS-39. My clinic, we have four MS-39s in testing rooms, and I have an MS-39 on my desk. So I have a slit lamp of the 20th century, and I have a slit lamp of the 21st century, which is the MS-39. And I cannot tell you how convenient that is to be able to just switch this over and examine a cornea and immediately look at it on the screen and direct the scan direction, find the exact scar or whatever I'm looking for, rather than waiting for a technician to do it and then having to bring the patient back. Anyhow, it's extraordinary. My financial interests include the fact that I do, this clicker isn't working. Oh, there it is. That, of course, I'm so happy to be part of the consulting body for the company. The first thing we're going to talk about is this little device. Okay. Now, the nose is a little optical lens, telescope, if you like. Okay. And you just screw it in to the middle of the pseudo system. And what it does is it changes the optics of a scan pattern from a rectilinear scan to a pericentric scan. And there are some reasons why sometimes you would want to use a pericentric scan. But you see that the angle of incidence can be more perpendicular to the corneal surface. And that means that you don't lose resolution in the periphery, which you do on a curved surface if you have a rectilinear scan. So it's a double-edged sword, because one of the disadvantages of exact perpendicularity to the corneal surface is that you get a bright sunlight reflection, right? It's like a Purkinje image, if you like. So actually, you don't really want to be, with ultrasound, it's fantastic to be perpendicular. Like with the Insight 100. But with optics, you don't want to be exactly perpendicular, or you would just see a huge bright sun and nothing else, because all you get is excess signal. So I just want to show you examples here. We have the Pentacam OCT also, and the Pentacam OCT is actually a similar system in that, but in this case, the scanning device actually moves in a pericentric way. Whereas what we're doing is we have a rectilinear scan mechanism, but we're converting it into a pericentric system with a lens. And as you can see, the choice that we had for an anamorphic image was to fit the front surface to the flat. And therefore, every other curvature beyond that is a relative curvature to the front surface. Rather than having to look, well, the curvature of the front surface is this, so the curvature of the back surface is a little bit more than this, yeah? So we zero out the curvature of the front surface, and then we stretch the z-axis as much as possible. So you can see that you get extraordinary detail inside the cornea. Of course, it's optics, so that means that you get a reflection, a Purkinje type reflection in the middle, because that's the exact perpendicularity. But also, you get more scatter. If you look in the middle of the stroma, there's more reflection, there's more backscatter from the center. It's not that the center has more haze. It's just an optical effect of the angle of incidence, right? The thing about the way that CSO has chosen to do pericentric scanning is that image that you see of the cornea, that image is part of that image. So the resolution of the new faster scanner device, the MS-39, actually gives us 16 millimeter scans for all scans with that level of resolution in the cornea. So no longer with the newer device no longer do we have to do a 10 millimeter scan for cornea and epithelium, and a 16 millimeter scan or a 25 millimeter scan for anterior segment diagnostics. So in one scan, we're able to get the entire anterior segment. This is obviously an aphakic eye or a pseudophakic eye. And just to say, you know, we're now getting into efficiency in workflow, because in the past, I would have to do several scan sets. And now I do a 1 second scan on each eye, and I'm ready to go for analysis. So just so that you can see telecentric scanning versus pericentric scanning. So rectilinear versus, and that little device is screwed in to the middle of the cone, and that's all it is. It's very easy. Now, what difference does it make? Why would you do this? Well, when you do a pericentric scan, you actually do get much better resolution in the periphery. So this is the same cornea now, scanned with the nose in place. And what you want to be looking at is the periphery. So when we compare the periphery of the cornea with rectilinear scanning to pericentric scanning, you can see that the epithelial interface, front and back, is much less resolved if you're doing rectilinear scanning than if you do pericentric scanning. Okay, so that's the purpose of having pericentric. It's not, like I said, it's not necessary to use it all the time unless you need higher resolution in the periphery. So, you know, it's an option. So not want to make a big deal out of it, but at least it's possible now to do that. The other thing is that, as many of you who have used the MS-39 now for years, you have seen gradual improvements in the segmentation of the epithelium. And, you know, over time, it's become better and better and better. And so that you know, the reason why I'm very confident about the epithelial thickness measurements from the MS-39 is that they're calibrated to the Insight 100 high-frequency ultrasound scanner, because that is the gold standard for accuracy. Yeah, and there's an explanation, very easy explanation to say why that is. But so when we do scans with both devices, we get the same results, and that's very helpful to us because obviously OCT is a lot easier to use than high-frequency ultrasound. But now we're finally at the point where the number of times that we're going to have to reanalyze a scan is going down. This is what we would have to do manually for a complex cornea. We would have to literally, this is a technician, one at a time. And if you look at the scan before it's wiped out, the detection algorithm was not that good at high frequency noise. And so this is what we have to do for a highly, pardon me, a highly complex cornea. And then we would get an accurate epithelial map. So the latest iteration of the epithelial segmentation on this cornea would give you this map. The same cornea reanalyzed now gives you this map. So these are not totally different, but they are a bit different. And when we're talking about transepithelial PTK, this makes a huge difference, because where you remove stroma from while you're doing a PTK is what creates the shift in refraction as a result of the transepithelial PTK. So having this information actually helps us understand what's going to happen to the cornea when we do a PTK repair through the epithelium. So just to show you examples of this exact cornea, left versus right, and now it's top versus bottom. The original algorithm, you see, would skip over very high frequency deviations. This new algorithm is very, very high fidelity in terms of following the contours. Yeah, you see that? So it's actually, you know, going to be, again, a workflow issue. It's going to give us a huge time saving when we want to look quickly at a very abnormal cornea. Yeah. So, you know, here's another example where the original algorithm would look like this, and the new algorithm, that's not a big difference. But if you look at the numbers, I can't see at this angle, but you know, 59 microns just to the right of the center. You can see here, you know, very, very subtle waves that are missed by an algorithm that's more of an expert system. There's another example. Very, very subtle waves that are missed. Yeah? And if you don't go back and reanalyze these things with the old algorithm, the one that you have right now, I'm calling that old. If you don't go back in cases where you really need accuracy, you will find that the device sometimes doesn't find the right interfaces. This is an example of a case where it's a completely different result, yeah, by analyzing. And why is that? Because the algorithm picked up the flap interface instead of Bowman's. And it does that sometimes. You have to, question yourself when you see an epithelium that looks very even and is very red. This new exact same case automatically picks up Bowman's exactly. Yeah. So that's the other thing that's improved. And the third thing that we wanted to talk about was a noise reduction system. And this is an algorithm that means that we get the same quality of scan by looking at one scan than if we were doing 10 scans and then auto-correlating the images. So what this means is that we don't have to do, 5 scans to get a high-resolution image. We can now do 1 scan and get a high-resolution. This is a single scan, and there, if you're in B-scan mode, if you would do a horizontal B-scan and just took one of the scans, it would look like this. But if you allow 5 scans to autocorrelate and reduce the noise, you would get a better looking scan. Now we get this, which would normally take autocorrelation with 1 scan. So we're really able now to see a much denoised system that can then bring out the interfaces for us. So those are the 3 new elements that are in the new software. And obviously the newer device that has the axial length measurement is a step above because of the speed of scanning. And therefore, the fact that you can do everything with a 16 millimeter scan, you don't have to separate repeating a 10 millimeter and a 6 millimeter. Now, everyone knows the Swiss Army knife, and so for me, this is the Italian Swiss Army knife, because before the MS-39, for me to diagnose keratoconus in a normal topography, I would have a normal topography, and I would have to look at the back surface, and I would have to try and correlate the back surface visually to the epithelial mapping. And this device was the first time that we could have all of these maps simultaneously acquired so that I can look at the epithelial profile and the back surface in one go. And obviously that is not just more convenient, it's actually more accurate because all of these points come from the same scan set. Being able to do all of this at once was a godsend for us. It was really fantastic. The second thing, as we've spoken about before, is effectively the statistical analysis of the cornea in terms of probability of keratoconus, given all of the parameters. All of this work was done by our colleagues in Italy, our ophthalmologist colleagues in Italy. And then, as you know, we designed this panel, which is the cockpit. And the first thing that your eye does is it goes to the epithelial profile and then the back surface. And then you look at the correlation between those two, and then you can really almost instantaneously tell whether a cornea is normal or not. And then the anamorphic scan, which can show us the exaggerated posterior curvature. We also use this 4-scan display where we put epithelial thickness at the top and the posterior elevation versus normality at the bottom so that we can compare these. This is an obvious keratoconic, but the device is particularly special because it's good at detecting keratoconus when the tomography is normal, when the shape is normal, because the epithelial profile reacts to any stromal surface irregularity. So, as you know, we can measure stromal thickness alone, and here's an example of a cornea that had corneal refractive surgery, and this is the stromal thickness. And the difference map between the 3-day map and the pre-op is 67 microns, but the lenticule thickness was 83. So that tells you how much edema there is in the stroma. Over time, the difference map changes. This is 5 months minus pre-month, and it's 83 versus 79. So in other words, we're able to actually measure the stroma separately. Yeah. Looking at peripheral scars and measuring the depth of the epithelium so that you don't create a flap or do a smile that is inside the epithelium. If the epithelium is very thick, you can then measure the density you estimate the density and decide whether you have to change your energy parameters when you're trying to cut through that. The fact that we can obviously look at the anamorphic image here's a Hansatone flap. The fact that you can scroll through a very complex cornea. This is a cornea that had, I think, about 35 minutes of smile lenticular extraction attempt. And as you can see, the surgeon left everything in place. And that doesn't look horrific in the horizontal, but as you scroll through the different, So as we scroll through, you're now looking, and I'm doing this at my desk, right? This is the patient is in front of me. I do the scan, and I'm looking at the patient's anatomy in the fourth dimension, right? Which is the cross-sectional dimension. So this gives you a massive amount of information about where you're going to try and go in, because you're not going to be able to go into the false plane direction. You're going to be able to find the lenticular edge from the part that wasn't separated, and then go in and find the way of separating. This is the full, another case actually. You can zoom out and make the window nice and big, and you can really decide where are these interfaces, where do I have to go, how am I going to get this lenticule out? Yeah? Really great. This is a thinner 8mm flap, and this is a wider 9mm flap around it. As we do sometimes, we have a wider, deeper option. We can measure the flap thickness, not in a massive resolution, but, oh, sorry, can you run the video on this? Yeah, that's right. Yeah. So, yeah, thank you. So you select the cap display. It gives you 9 windows, and then you place one spot into the interface where you see it, and it gives you a low resolution but indication of the flap or cap thickness. And we use this to plan circle procedures, because trying to find the junction and program all of the parameters of a circle procedure in SMILE, it's made more reliable if you actually have a map of the thickness of the cap. What else? Exactly. So this is a PRK a few days, like maybe 2 days out, under a bandaged contact lens. So there's the bandaged contact lens here, and this is the epithelium. And sometimes it's hard to see where the epithelium is, not in this case, but you can actually watch the epithelium. Now, where I've used this in a very helpful way is when you get delayed epithelial closure. So you have a case where you've done cross-linking and you've done a little bit of ablation. And sometimes with cross-linking, you get delayed closure. And so if you want to know whether it is stopped growing or whether it's still growing but just very slowly, you actually can do it in microns by measuring on the image. And that can mean the difference between, switching to PRP drops or an amniotic membrane and just being patient and leaving the bandaged contact lens in and waiting a little bit longer. Sometimes epithelial ingrowth is completely invisible at the slit lamp, but we can actually pick it up on OCT. And so when I do my 1 week check after flap lift enhancement, I always look at the OCT. I actually rely on the OCT now more than myself at finding whether there's any ingrowth anywhere. Because you can have a very thin sheet of ingrowth like that, which is invisible, and you say to the patient, everything's great, we'll see you in a month, and then they come back with a necrotic pool of epithelium because it actually continued to grow in from the edge. And this is another example. You can see a tiny, tiny little leak there on post-op day 1. And then a few months, at the 1 week mark, we can actually detect the epithelium in that location. Yeah. And again, little seepage at the end of the wound, and you can verify it with an OCT. Right there. Yeah. Being able to zoom in and do these anamorphic scans means that we can also see little bits of flap melt very, very nicely. Being able to follow a wound infection over time, you want to know whether, at the slit lamp, you can see diameter, but it's harder to see whether it's progressing downwards or upwards. And so monitoring with OCT means that we can actually check that the reflectance is decreasing or not diving into the anterior chamber. Of course, we have the corneal wavefront and all of the ways that we can manipulate this. One of the neat things about the corneal wavefront is that we are able to look at it based on the vertex of the cornea, which is the corneal wavefront, but you can also choose to look at the corneal wavefront based on the center of the pupil, which is a different calculation center, and that allows you to compare it better to a whole eye wavefront, which is always calculated from the center of the pupil. Yeah, with the Osiris, actually, they also allow you to calculate the whole eye wavefront from the vertex, which is very unique, actually, for wavefront sensors. But it's more relevant to optics. We have dynamic pupillometry over time and in different lighting conditions. There is an algorithm to tell you about how to put, what kind of ring to put in. This is for plastic rings. This was developed, I think, with Jorge Alio's group. You have a non-contact breakup time analysis topographically. So essentially, this device is literally, if you say, is it the only device I need? Well, no, because you also need the wavefront, and for us, we also need the posterior chamber with ultrasound so that we can do safe ICL sizing. But really now, what used to be a testing room for us with 7 devices has become essentially 1 plus a couple of others. The new algorithm, amazing at picking up the interface, and so I hope you enjoy that because it's really going to cut down some of your analytical time. So thank you very much.